This is the video for section 11.2 on series or infinite series, and the point of this section is for us to talk about what it means to possibly add up infinitely many numbers. And before we talk about the technical details, I want to motivate this with a couple of examples. For the first example, I want us to consider the decimal expansion for the number e. And I'm picking e because it's a fancy number, but any decimal expansion we can do this for. So e we can write as 2.71828 ... And this decimal never terminates and it never repeats. And the way that I want us to think about this is by adding up the decimal digits. So I can get e as adding up the first decimal digit, 2.00, plus 0.7 plus 0.01 plus 0.008 and so on. Okay? And so the point here is that this is exactly what a decimal expansion for a number means. It means that I am taking the fractions that are determined by the digits, accounting for the place of the digit, and adding up that infinite series of numbers. For another example, and this is one that we'll look at several occasions in the lecture, is to look at the numbers 1/2 plus 1/4 plus 1/8, 1/16. So I'm adding up the fractional powers of 2. And I claim that when you do that, what you get is actually 1. And we'll see a couple of reasons for why this is true as we move through the lecture. I'll give you a geometric explanation for this. And so the geometric explanation is that if I take a square of unit side length, then cut it in half, and that area of the first piece is exactly 1/2. If I cut the remainder in half, then one of those pieces has area 1/4. And if we cut the remainder of that in half, then one of those pieces has area 1/8. Cut that remaining bit in half, one of the pieces has area 1/16. And if you do this process forever, then you end up adding up all the pieces of area inside this unit square, which has area equal to 1. Okay? So the point here is that there are a couple of basic motivating examples that show why it makes sense to add up infinitely many numbers sometimes. Okay? So the general idea is that if we add up smaller and smaller numbers, infinitely many of those, we can possibly get a finite number. Okay. So before we move on, let's have a little bit of notation. So if I write the summation I equals 1 to n of a sub I, right? So I'm using the notation that we already saw for sequences, the sequence AI, that this is shorthand for the first term of the sequence plus the second term of the sequence all the way up to the nth term of the sequence. Okay. And if I vary that by considering the sum I equals 1 to infinity instead of stopping at n, then I have, with the AI term, that's a1 plus a2 plus all the way up to an, and then I keep going, adding up all of the numbers that are occurring in that sequence. So this is called the second sum is called the infinite series, and is sometimes denoted by S for series. And this first sum is called the nth partial sum of the series, and sometimes we denote this by Sn. And it's called the nth partial sum because we stop partway through the series, as opposed to in the full series down here, we keep on going. Okay. Now, here it's important to make an important distinction in the terminology that we have two words that are very similar to one another. We have the word sequence, which is what we have for a list of numbers. For instance, 1/2, 1/4, 1/8, 1/16, etc., with commas in between. And then we have the series associated with that sequence, which is the sum of those numbers. For example, 1/2 plus 1/4 plus 1/8, and so on. Right? And notice the difference in notation. Here I would use the curly bracket, an, to denote the list of numbers, and here I would use the summation notation. We should also make a note about the subscripts, the indexes on our summations. In this first partial sum, I start with I equals 1, and that corresponds to the fact that I've started with the term A1, and I end with the number n, and that corresponds to the fact that I've ended with the nth term. Down in the infinite side, if I start with I equals 1, then I start with A1, and if I go to infinity, that's telling me that I go on and on in my series forever and ever. Okay? And you should notice that up here I have the index I, which corresponds to the fact that I'm using the subscript I for my terms in my series. Down here I'm using the letter N for the index, and that corresponds to the fact that I'm using the subscript N in my sequence. Okay? So we'll look at a variety of examples that use different letters and different indexing start points as we move forward. Okay. So getting used to the notation, for example, if I look at the summation, I equals 1 to infinity, let's actually do n equals, let's do I equals 1 to infinity of 1 over 2 to the I. Okay? So this is the summation that we wrote out before, 1/2 plus 1/4 plus 1/8, and so on. If we take the nth partial sum, so that's I equals 1 to n, 1 over 2 to the I, that says that I start with 1 over 2 to the 1, next I have 1 over 2 to the 2, so 1/4, and I keep on going until the last term is 1 over 2 to the n. So this finite partial sum stops. It's only a finite addition process, but the infinite one in the first line keeps on going. Now, one of the things that you'll be asked to do is to figure out whether or not a series converges. And here's how you do that in general, is you take this expression that we have and we're going to simplify it algebraically. And the way we're going to do that is we're going to put everything under a common denominator. And since all my denominators are powers of 2, I can use the largest power of 2 as my common denominator. So that'll be 2 to the n in the denominator. And when I put all those fractions under a common denominator, what I end up in the numerator is 2 to the n minus 1. That's because for the first term, I have to multiply top and bottom by 2 to the n minus 1. For the next one, I get 2 to the n minus 2 because I have to multiply the top and bottom of the next term by 2 to the n minus 2 in order to get my common denominator. I add all those up. For the last one, I don't have to multiply the top and bottom by anything in order to get the common denominator. Now, it is a fact, and one that we've certainly seen in Math 1060, if not in 1080, that when you add up the powers of 2, 1 plus 2 up to 2 to the n minus 1, that is the same thing in the numerator as 2 to the n minus 1 divided by 2 minus 1. And I'll give an explanation for that in a second. The denominator stays the same, and what we find is that 2 minus 1 is 1, which means that that bit in the numerator disappears, and we simplify to 2 to the n minus 1 over 2 to the n. Or if you like, 2 to the n over 2 to the n minus 1 over 2 to the n. So this partial sum that I have here is equal to 1 minus 1 over 2 to the n, right? Because it's equal to this thing here. And now what's the point is that this term, as n goes to infinity, this difference goes to 1 minus 0, which is 1. And so what we conclude is the limit, as n goes to infinity, of this sequence of partial sums that's the same thing as the limit as n goes to infinity of 1 minus 1 over 2 to the n. That's equal to 1. And that's exactly what we found that the infinite series converges to. Okay? So, we make a definition. That definition is that we consider the nth partial sum, summation I equals 1 to n of a sub I in general, and we say if the limit as n goes to infinity of Sn converges and is equal to L, so I'm converging to some finite number, then the summation I equals 1 to infinity of the a sub i's, the infinite series, is equal to L. And in this case we say that the series converges. And we say that it diverges when the sequence of partial sums diverges. In other words, we say that the sum from I equals 1 to infinity of our a sub I series is equal to the limit as n goes to infinity of the sequence of partial sums. And for a little bit of discussion and an example of this, you can see example number 1 in the textbook. Now, we are going to spend the most of this chapter, not just this section, trying to figure out ways to determine whether or not series converge or not, and figuring out when they do converge, what they converge to. So what is that limit? What is that infinite sum? And we'll see a couple of examples of this in this section, starting with the geometric series. Now the example you should keep in mind is the one that we've been looking at, and that's the summation I equals 1 to infinity of 1 over 2 to the I. Right? So the fact that it's a geometric series is being reflected in the fact that I'm using a power of a fixed number as my increment. And so a general geometric series is of the form summation I equals 1 to infinity of a times r to the I minus 1. So I have a fixed number a that's being multiplied by powers of another fixed number r. And so the first bits of the series look like this. It's a plus a times r plus a times r squared plus a times r cubed, and so on. And the book goes to explain in example 2 that we know exactly when these types of series converge and diverge. So we get that the summation is a over 1 minus r, so it converges precisely when the absolute value of r is less than 1. And it diverges in all the other cases. So for example, if we consider the following sum, so I want to look at 4 plus 3 plus 9/4 plus 27/16, and so on. And so what we have to do in this example is we have to recognize this as a geometric series. And the way we do that is by looking at the pattern that occurs when we move from one term in the series to the next term. For example, between the numbers 9/4 and 27/16, we see that we multiply the numerator by 3, and then we multiply the denominator by 4. So that's the same thing as dividing by 4. And so in what that amounts to in total is that we are multiplying by the fraction 3/4. And if you check, this is exactly the same pattern that's occurring when you move from 4 to 3. That's obtained by multiplying by 3/4. And when you move from 3 to 9/4, that's the same thing as well, multiplying by 3/4. And so what we conclude from this is that r equals 3/4, which we see is in absolute value strictly less than 1, and a, right, which is always the first term that we have in our geometric series, is exactly 4. So r is the number that we multiply at each step, and A is the first term that we have in our series. And I should say that the letter R is used, that's short for ratio. Because if you take the ratio of successive terms in the series, you get R each time. Now, the fact that the ratio in absolute value is less than 1 tells me, by the fact that we have above, that the geometric series converges. And in fact, it tells me exactly what the series converges to. I take that number A, which is 4, and I divide it by 1 minus the ratio, which is 3/4. And when you simplify that, that's 4 over 1/4, which is the same thing as 16. For other examples like this, you should see examples 3, 4, and 6 in the textbook. Now, we can use this similar idea in order to take a repeating decimal and write it as a fraction, as a ratio of whole numbers. So for example, I want us to look at the number 2.9178178178 ... Right, so this would be written as 2.9178 with a bar over the 178 to indicate that that's the repeating part of the decimal, the 178. And we want to write this as a ratio of whole numbers. Okay? And the way to do this is to recognize it as a geometric series. And we'll do that as follows. So what we do is we need to write this repeating decimal as, first we start with the non-repeating part, and then we add the first repeating part, and then we add the next repeating part, and we add the next repeating part, and so on. And what we want to do is we want to, after we deal with the initial part, to recognize that the pieces of the repeating parts can be written as fractions quite easily, with denominator equal to a power of 10. So here we have 178 times 10 to the minus 4. Here we have 178 times 10 to the minus 7. Here we have 178 times 10 to the minus 10, and so on. And when you now take that 2.9 and that 178 times 10 to the minus 4, this is going to be our A. And so what we need to do with the rest of the terms is to factor out a factor of A and track the remaining quotients. So what we get here is 178 times 10 to the minus 4 times the quantity 10 to the minus 3. And the next one, when I factor out the 178 times 10 to the minus 4, I'm left with 10 to the minus 6, and so on. And now, this number is going to be my R. And you can check, the next one in line is exactly our r squared. So I have exactly a sum that's of the form of a geometric series. That means that I can write those bits that are underlined in terms of my a over 1 minus r formula. So we get 2.9 plus 178 times 10 to the minus 4 divided by 1 minus 10 to the minus 3. Now this is a messy fraction. Whenever you have fractions with negative exponents in the numerator or denominator, you want to clear the powers from the numerator and denominator, so we'll multiply top and bottom by 10 to the 4th. I'll also convert that first number 2.9 into a fraction, so that's 29 over 10. And I add to that 178 over 10 to the 4 minus 10. That's what happens when I simplify the numerator and denominator after multiplying top and bottom by 10 to the 4th. And when you simplify that new denominator, we have 29 over 10 plus 178 over 9990. And when I put those under a common denominator, I have 29 times 999 plus 178 over 9990, which simplifies, you can check, to 29149 over 9990. Another example of this you can see is in example 5 inside the textbook. This next type of example is one that's called a telescoping series. And we'll figure out the convergence properties for this series by doing lots of cancellation. So the specific example that I want us to look at is the summation n equals 1 to infinity 1 over n plus 1 times n plus 2. And notice that I'm using the index n here instead of I. The process still goes the same, and we'll see how this looks in just a second. After we recognize that the term of this sequence can be broken into two pieces by partial fraction decomposition. Okay, and this is going to be a good technique for evaluating series that have rational function terms. So when we write out some of the terms of this series, we have, so when n equals 1, we get 1/2 minus 1/3. When n equals 2, we have 1/3 minus 1/4. When n equals 3, we have 1/4 minus 1/5, and we get 1/5 minus 1/6, and so on. And what you see is that at every step, here I have a minus 1/3, here I have a plus 1/3. Here I have a minus 1/4, here I have a plus 1/4. Here I have a minus 1/5 and a plus 1/5. Minus 1/6, and the next bit would be a plus 1/6. So this is the infinite cancellation that I was talking about before, and we find that the total sum of this series is equal to the one term that remains, which is 1/2. Okay. And another example of this is in the textbook, which you can see is example number 7. Now, we have just a couple more items left in this section. The first of these is what's called the test for divergence. So the test for divergence starts with a theorem, and the theorem says the following: if you have an infinite series of terms that converges, then the terms of that series when you take the limit of those have to equal 0. Right, so this goes with what I said at the beginning, that for a series to make sense, the only thing that we can do is possibly add up smaller and smaller numbers. So the conclusion from this theorem is the important thing. Sorry about the mess. This is the so-called test for divergence. Which says, so this is what's called the contrapositive of the theorem. It says that if you have a situation where the limit as n goes to infinity of an is not 0, right? So either you get a finite limit that's non-zero, or you get that that nth term sequence diverges, then the series that you started with must also diverge. Okay. So let me give you an example of how this works and how it doesn't work. So for this one, I want us to look at the series k equals 1 to infinity of k times k plus 1 times k plus 2 over k cubed plus 5. Okay. Now the fact that we're using k's here instead of n's, again, that's just a change of index like we were using i's before. And so you look at this and you say to yourself, okay, I can't see how that would be a geometric series, because it's not. And I can't see necessarily how to turn that into a canceling telescoping situation. So what I do is I look at the limit as k goes to infinity of the kth term, and you look at that, and there are a couple of ways that you could approach it. The numerator, I have a polynomial in k of degree 3. There are 3 powers of k at the highest power in the top. The denominator, I have the highest power of k is 3, and so my limit is going to be the ratio of the leading coefficients. You could also check that this limit converges by looking at it as a function of x and using L'Hopital's rule, or multiplying top and bottom by 1 over k cubed. And what's the point is that here my nth term limit is non-zero. And so the conclusion that I get to make by the test for convergence is that my series diverges by the test for divergence. Now, another example of this that's really important for several reasons, this is the so-called harmonic series. And the harmonic series is the following. So we look at the summation n equals 1 to infinity of 1 over n. So I'm looking at 1 plus 1/2 plus 1/3, and so on, with no powers, right? This series actually diverges. And this is an important example to keep in mind, and we'll see a couple of reasons why this is true. You can see, for instance, in example 8, a nice explanation for why this diverges. The point is that you analyze the nth partial sum, and you show that that can't be equal to a finite number. Now, the thing about this example that is important to keep in mind is that when we take the limit as n goes to infinity of the nth term, we do get 0 for this one, right? 1 over larger and larger numbers gives me a limit of 0. And so the point of this example is that we need to be careful when we're using the test for divergence because you can only conclude from the test for divergence that a series diverges. You cannot make any conclusions about convergence. You might want to say that this example, because the limit of the nth term here is 0, that I could conclude that this series converges, but we can't, right? The example shows that it diverges. So you have to be very careful about what happens when you apply the test for divergence. Okay, one more very brief topic for us to talk about, and that's the fact that the normal rules for sums can be translated to series. So rules, let's do that in a different color. So if we have two series, summation n equals 1 to infinity of an, if that converges and the summation n equals 1 to infinity of bn also converges, then the series n equals 1 to infinity of an plus bn also converges, and in fact its sum is equal to the sum of the first series plus the sum of the second series. So the rule is that if you have two convergent series, then the series of the sum is the sum of the series. And it is absolutely crucial that you start out with two convergent series. If you try and do this with divergent series, things can go bad, and you can't really draw any good conclusions from that. We have similar rules for the series of difference terms and for the series of constant multiple. Right, so the sum of the differences is going to be the difference of the sums, and the sum of the constant multiples is going to be a constant multiple. So I can factor out a constant. And you can see an example of this in the text in example 10. So this is the end of the video on section 11.2 on series.